Hello, class. Wait about 30 more seconds, and then I'm going to get started. All right. Hope everyone's doing well. Plug in my document camera. Okay. So today we are going to start talking about electric circuits. Last time we talked about the electrical force. The electrical force is K, Q1, Q2, absolute value over R squared, where the rule for the direction of the force is that opposite charges attract, like charges repel. And this constant K is called the Coulomb constant, and its value is 9 times 10 to the 9th Newton meter squared per Coulomb squared. Okay. We learned that the amount of charge that something can have is an integer multiple of the fundamental charge, where the fundamental charge is the charge of a proton, and that value is 1.6 times 10 to the minus 19 coulombs, plus 1.6 times 10 to the minus 19. And then the last thing we learned about was electric current, which is denoted by I. All right. And the electric current is the charge that flows divided by the time it took to flow. The units of electric current are called, well, if we just look at this, it's amps or coulombs per second, which is called the amp, which is abbreviated A. All right. So electric current is the rate of flow of charge. So when we're talking about circuits, even though the motion of charges within a circuit are described by electrical forces, we don't really talk about the electrical force, Coulomb's law, when we're talking about circuits. So there's two key variables that we talk about when we're talking about electric circuits. The first one is electric current. Okay. The second one, and that gets us into today's lesson, is called electric potential. AKA, also known as voltage. Which is, so I will, since we're talking about circuits, I'll be referring to it mostly as voltage. It's denoted by V, and what voltage is it's a force in the circuit causing current to flow. Okay, so you could think about voltage as the cause and electric current as the effect. So if you have no voltage, no current will flow. Current won't just flow spontaneously. There needs to be a voltage in order to have current flow. Okay. So yeah, the voltage is the cause. The units of voltage are called volts. All right. And volts are abbreviated by V. So you can have kind of confusing expressions, like you can have V equals 12V. So what that means is that the voltage is 12 volts. Okay. So you want to keep that in mind. You know, you don't cancel out the V's and get 1 equals 12. Okay. On the left-hand side, V is representing the quantity voltage, and then on the right-hand side, it's the unit volts. Voltage is provided by a source. Okay. So there are a number of different sources that you could encounter that provide voltage. So, for example, a power outlet, or for example, a battery, or for example, a solar panel, or for example, a generator, something like that. So there are a number of different devices that provide a source of voltage. And these all have different voltage outputs. So a power outlet is going to provide 120 volts. That's standard for power outlets in the United States, okay? And I think in Canada as well. But yeah. And then in the United States, you also have 220 volt outlets. All right, so this would be more for like, you know, if you have some power tools, oftentimes power tools need more than 120 volts in order to run properly. So if you have some big equipment in your garage, you might have a 220 volt outlet in your garage. because big machines draw a lot of current. Batteries are typically going to be some multiple of 1.5 volts. And that's kind of standard. I'm not sure why that's the standard. It would be interesting to look up why 1.5 volts is kind of the standard. But a AA battery is 1.5 volts. A AAA battery is 1.5 volts. A C battery is 1.5 volts. A D battery is 1.5 volts. So the only difference between all of those is not the size of the voltage. It's just the amount of time that it can provide that voltage for. So when a battery is placed in an electric circuit, it does its thing, but as it's doing its thing, there's a chemical reaction happening inside the battery. And so you have reactants turning into products inside the battery. And the battery is dead when all of the reactants have turned into products. So you can't have that chemical reaction happening anymore. Okay? And then of course you also have like 9-volt batteries, which are used in like camping lanterns sometimes. You have 12-volt batteries, which are used in cars. Cars have 12-volt batteries. So yeah, I don't know why, but they're always in multiples of 1.5 volts. Solar panels can output a variety of voltages, and that voltage depends somewhat on the level of insulation. So, you know, how much sun is there. Okay. But for the most part, a solar panel outputs a pretty consistent voltage, and it's the current that changes with the amount of sun. Generators are going to output 120 volts because they're used to power your house, so it outputs the same voltage as your house. Okay? So these are the two fundamental circuit quantities: voltage and current. All right? Now, so let's learn how to draw circuits. Okay? So if you just draw a line, that's a wire. All right? So lines represent a wire, which is basically a pathway for electric current to flow. You can draw wires that fork. Okay, so if you want to express the fact that the wire is splitting up into multiple parts, you put a little dot, and then you just have the wire split like that. So this is a wire that's splitting into 3 pieces. Okay, so that's perfectly acceptable. You can do that. You can have things like switches. So a switch looks like this. That's a switch in the open position. A switch in the closed position just looks like this. And then you can have, if I draw something that looks like this, this is a battery, which basically, remember, a battery provides voltage. So in order for anything to happen in a circuit, you need to have a battery or some kind of source of voltage, because voltage is the cause of current flowing. Okay. And so you can see that the symbol for battery is like long line, short line, long line, short line. And the longer line side is the positive terminal, and the shorter line side is the negative terminal of the battery. And the current flows out of the positive terminal. Okay? And it flows in to the negative terminal. So that's the direction of charge flow. All right? And then there are various symbols for different devices. So, you could have this is the symbol for a light bulb. Okay. So, yeah. So let me draw just like a really basic circuit diagram. So this is a circuit, draw that a little bit better, with a switch, a battery, and by convention you usually put a plus on the positive. You don't need to put a negative on the negative terminal of the battery because it's just the other terminal, okay? But by convention, okay, so we have a battery connected to a switch, connected to a light bulb, connected to the negative terminal of the battery, okay? So if you think about how many wires would you need to build this circuit, you would need 3 wires, because you would need this wire right here, you would need this wire right here, you would need this wire right here, okay? And so right now, with the switch in the open position, current can't flow because, current can't flow because the switch is open, so there's no pathway for current to flow. But if you close the switch, okay, then electric current is going to begin to flow out the positive terminal of the battery, and it's going to go through the light bulb. So it's kind of like a lazy river, okay? Right? If you've ever been to a hotel or something with a lazy river, it's like the flow is just going around and around as long as the battery still has reactance inside it. It just goes around and around, and the current passing through the light bulb is going to make the light bulb shine. Okay? So, the question is, how much current will flow? Okay? So, for example, let's say this is a 12-volt battery. How much current is going to flow in this circuit? Well, this leads us to what is called Ohm's Law. Okay? And Ohm's Law is very easy to remember. It's V equals I times R. Verb. All right? Where V is the voltage of the battery, or I'm going to say the source, voltage of the source, okay? I is the current flowing out of the source. And R, and this is a new concept, is called the resistance of the circuit. Okay. So the idea is this light bulb has a certain resistance to current flow. Okay. So this is main equation 1 for today. So, all right. If we rewrite Ohm's law and we say V over R equals I, that's the same equation, right? I just divided both sides by R. You can see that as the resistance increases, that's going to make the denominator bigger, which is going to reduce the current flow. So more resistance means less current flow. Okay? So that depends basically on the type of light bulb you have. Okay? You can have different light bulbs. The unit of resistance is called the ohm, OHM, which is represented by the Greek letter omega. Okay? So that's a capital Greek letter, omega. Remind me after class, and I will share with you some ohm puns. I have a lot of good ohm puns. All right. So, if we want to talk about that, so there's a device called a resistor. Okay. Which is something in a circuit that provides resistance. Okay, so a light bulb could be thought of as a resistor. Okay, it's a resistor that does something useful in the process of resisting. Okay, and so the circuit symbol for a resistor is a jagged line. So that is a resistor, and we would normally write the value of the resistance next to it. Okay. So the resistor. Now you might think, well, what is a resistor? Well, the resistor could represent something doing a useful task. Okay, so for example, this resistor could represent an appliance in your house. This resistor could represent an electric motor. It could represent a light bulb. It can represent a number of different things, okay? So it could represent something doing a useful task. But we also have resistors that don't do anything. We just put them into the circuit, and they don't light up, they don't lift things, they don't do anything really. So there are also resistors that do nothing except control the amount of current flow. So that is oftentimes how resistors are used. That if you're designing a circuit and you want to make sure that the circuit has a certain amount of current flowing in it, you can use a resistor that doesn't do anything to achieve that. Okay, so the only thing it's doing is slowing the flow of current down to the level where you want it to be. All right? So it provides a level of control within a circuit. So let me draw the basic circuit. So the basic circuit just looks like this. So this circuit would take two wires, a resistor, and a battery. Let's say it's a 12-volt battery, and let's suppose that the resistor is a 2-ohm resistor. So if I wanted to know how much current is going to flow out of the battery when you hook up this circuit, I would simply use Ohm's Law. Okay? And so I would say V equals I times R. All right. The voltage provided by the battery is 12 volts. The resistance of the circuit is 2 ohms. So I have I times 2, and the current that flows is going to be 6 amps. Okay? So again, we're using the resistor to control the amount of current flow. All right? Now, resistors can be combined in various ways. All right. So let's talk about some of the common ways that resistors, or things in general, circuit things in general, can be combined. Okay. So one of the ways that resistors can be combined is if is called a series connection. All right. And a series connection has one resistor connected to the other by a wire. Okay. So it's like a chain of resistors. Okay. All right. And so it turns out that when you combine two resistors like this, it is equivalent to a single resistor. Okay, so maybe this is one light bulb and this is another light bulb. Okay, then from the perspective of the battery, if we have two light bulbs in a circuit, the battery just sees it as one resistor. Okay, and so we're going to call that equivalent resistance. So even though it's two separate resistors, it behaves in the circuit as a single resistor, which we will call R sub S. Okay, and R sub S is equal to R1 plus R2. Okay, And you could have multiple resistors in series. So you could have 3 resistors in series, like this, or any number of resistors in series. And however many you have in series, you just add up the resistances. Okay? So let me tell you a little trick to determine if things are in series. Okay? So here's a trick. If you can go from one to the other, without the wire forking, they are in series. Okay? So that's like the way to tell if 2 things are in series. All right? So for example, if I go from 1 to 3 passing through the circuit, you can see that there are no forks in the wire. Okay, it's just I don't have any branches going off to the side. So 1 and 3 are in series. But what if I had 2 resistors? So 1 and 2, and then in between them, the wire forks. So in other words, the wire splits in 2 or more pieces. Maybe it splits into 3 pieces. This would not be a series connection, and I'm just going to say these go off somewhere else, because the wire forks along the path connecting them. Okay? So these are not in series. Okay? So yeah, if you have 2 resistors in series, that's the equivalent resistance of them. The other common connection that you will see is called a parallel connection. And a parallel connection has a wire, and the wire forks. Oops. I got ahead of myself there. The wire forks, and then it goes through 2 resistors, and then it comes back together. Okay, so R1, R2, like that. And so this is equivalent to a single resistor, which I will call R sub P for parallel. So again, from the perspective of the circuit, these 2 resistors act as if they were a single resistor. Even though they have their individual identities, from the perspective of the voltage source, they might as well just be lumped together into one thing. Okay? And the value for R sub P is determined by this rule. 1 over R sub P is 1 over R1 plus 1 over R2. All right? And this rule generalizes. So if you had 3 resistors in series, you would have the wire is branching into 3. So here we have this wire goes in and it branches into 3. 1, 2, 3. And so you would just continue this same pattern. So you'd have plus 1 over R3, etc. So you can have, just like you can have any number of resistors in series, you can have any number of resistors in parallel. So let me tell you a trick. If you can do a loop in the circuit, so sometimes I'll abbreviate circuit as CKT, with only two things. So in other words, only two resistors in it. They are in parallel. Okay, so for example, what if I had a circuit where it was like this? So a lot of times students get hung up on the word parallel, and they think that the resistors have to point in the same direction. But that's not the case. All right? These two resistors, even though one is horizontal and the other is vertical, they are in parallel. Okay? Because I can imagine going around this square loop in the center, and the only things in this, the only circuit, the only resistors are these two resistors, and so therefore they must be in parallel. Okay, so if I can do a loop in the circuit with only two things, then those two things are in parallel and I can combine them according to this rule. Okay, but let me give you an example of something that almost looks like parallel but is not. What if I had something like this? Okay, so 1 and 2, see, they're both pointed horizontally. It looks like they're parallel to each other, but they're actually not in parallel. Okay, and the reason is, if I wanted to do a loop and walk around this loop here, see how I can't walk around that loop without encountering this resistor as well. Okay, so the presence of this resistor means that these two are not in parallel, because I can't go around this loop with only those two resistors in the loop. Okay, but these two resistors are in series, right? Because I can go from this resistor to this resistor. There's no fork in this wire connecting them. All right, so that's how you identify series versus parallel. So how do we use this stuff? Well, let's do an example. Okay, so we got a battery right here. And then we got a bunch of resistors. Okay. So this is a 24-volt battery. We'll say that this is let's say 10 ohms, 5 ohms, 11 ohms, 3 ohms, 4 ohms, let's say 20 ohms, and 12 ohms. Okay. So why would you encounter a circuit like this? Okay. So you have to remember that each of these resistors is representing something that is doing something useful. Okay. So this battery might represent the voltage that's provided by Southern California Edison. And maybe this is an appliance. These are some light bulbs. And, this is a microwave, and this is a refrigerator, the air conditioning, whatever, okay? So all of these devices can be modeled by resistors, okay? And, all right, so they're modeled as resistors. And what we want to know is how much current is going to flow out of the battery. All right? And so what the strategy is we're going to use these series and parallel rules to step by step simplify it to a single resistor. So we're going to take all 1, 2, 3, 4, 5, 6, 7 resistors, and we're going to break it down using these rules step by step into a single resistor. Okay? So let's show how that works. Okay? So what we want to practice doing is looking at the circuit and identifying series and parallel. Okay? And so right away I identify that the 20 and the 12 are in parallel. How do I know that? Because I could walk around this loop in the circuit, that loop right there, and it only has those two resistors in it. So those two resistors are in parallel. So I can use the rule for combining parallel resistors. It's 1 over R sub P is 1 over 20 plus 1 over 12. Okay? So 1 over 20 plus 1 over 12 is 0.133. Okay? Now, oftentimes what people forget to do is they forget that this is the equation for 1 over the parallel resistance. Okay? So you have to do 1 over that to get the actual resistance. And I get 7.5 ohms. So these two combine to make 7.5 ohms of resistance. Then I can also see that the 3 and the 4, okay, are in series. Why? Because I can go from this resistor to this resistor through that wire right there, and that wire doesn't fork off in any other direction. Okay, so I can combine those. So R sub S is 3 plus 4, which is 7 ohms. Okay? So now what I'm going to do is I'm going to redraw the circuit, but these two resistors are going to lose their identity as separate resistors, and these two resistors are going to lose their identity as separate resistors. So again, where there were two resistors here, I am now drawing them as one, as a single 7 ohm resistor. And then whereas there were two, I am now combining them to make a single 7.5 ohm resistor. All right. So where do we go from here? Well, one of the things I can see is that now these three are in parallel. How do I know that? Because if I go around this loop, I encounter only those two resistors. If I go around this loop, I encounter only those two resistors. If I go around this loop, I only encounter those two resistors. All right? So all three of those are in parallel. So I'm going to use the rule applied to 3, which is 1 over r sub p would be 1 over 5 plus 1 over 11 plus 1 over 7. All right? And that's 0.433. But remember, I have to do the inverse of that because this is the equation for 1 over r sub p. So that's 2.3. R sub p is 2.3 ohms. And then the 7.5 is actually in series with the 10. Now, if I go this way, if I go from the 7.5 to the 10 in this direction, it wouldn't be in series, right? Because going from here to that location, the wire forks into 3 pieces. So there's forking if I go in this direction. But if I go in the other direction, I can get from the 7.5 to the 10. So even though they're not directly next to each other, they are in series, okay? Because if I go this way, there's no splitting of the wire along that path. Okay, it just stays one wire without any forks going off to the side. So I have R sub S is 10 plus 7.5 equals 17.5 ohms. So now I redraw the circuit again. And I can replace these two with a single 17.5 ohm resistor. Okay, and then I can replace these 3 with a single 2.3 ohm resistor. Okay, so now it's fairly obvious that these two are in series because this wire connecting them doesn't have any forks in it. So I have R sub S is 17.5 plus 2.3, which is 19.8 ohms. All right. So now I have a 24-volt battery and a 19.8 ohm resistor. So now I have reduced this big mess of a circuit down to a single equivalent resistor. So remember, these resistors all maintain their identities, but from the perspective of the battery, it looks like a 19.8 ohm resistor, okay? And so now that we have it to a single resistor, we use Ohm's Law, V equals IR. So it's a 24-volt battery, and it's a 19.8 ohm equivalent resistance. And that's the current that flows is 1.21 amps. Why is it useful to know what the current that will flow is going to be? Well, there's 2 reasons. Number one is if this is a battery, well, I can think of 3 reasons. If this is really representing a battery, then the current tells us how quickly the battery is going to be drained. So we could have some idea of how often we'll need to replace the battery. Okay. If this is representing a voltage source like the power lines, the power lines never run out of current, okay? But the current that you draw determines how much you're going to pay every month. So this could tell you something about what your electricity bill is going to look like, all right? The other thing that this has implications for is it would tell you how thick these wires need to be, all right? The more current a wire is carrying, the thicker the wire needs to be in order to not get too hot, all right? So, if you try to drive a lot of current through a really thin wire, that wire is going to get incredibly hot and it's a fire danger. Okay, so you want to know how thick do you need to make the wire. So those are some reasons why you might want to know the current flow. All right, so that's